Hi, everybody. We're just going to wait another couple of minutes to make sure everybody gets on. We'll start shortly. Okay, I think we'll get started. So welcome everybody to today's webinar. My name is Mary Beth Behrens. I'm the Director of Marketing here at Core ABI. And today's webinar is a joint effort with our partner Disti, and it's entitled From Detection to Display, Using Safety Critical Neural Networks in Automotive Applications. Presenting today is Lucas Friesick from the Core ABI side, and he's one of our FAEs. And on Disti side, we've got Chris Giordano, and he's Vice President of UX UI Technology. For questions, you'll see at the right-hand side of your screen, there should be a Q&A box. So feel free to submit a question at any time during the webinar. When we get to the end of the webinar, we'll start going through the questions during the Q&A section. Hopefully we'll have enough time to get through them all. If we don't, we can always reach out to you later. Okay, so without further ado, sit back and enjoy everybody, and I will pass it over to Chris.
Thanks a lot, Mary Beth. So thanks everybody for taking the time to attend. We're going to be talking, as Mary Beth said, about using safety critical neural networks and automotive applications. Specifically, the automotive application we're going to be talking about is augmented reality HUDs, heads-up displays. So real quick outline of what we're going to be covering between Lucas and I. So I'll start out with a real brief background on HUDs and AR HUDs. And then the different system setup for an AR HUD. And then we'll get into projecting 3D objects in the real world, real-time data updates. Then I'll hand it over to Lucas to have the discussion on functional safety and the importance of functional safety in AR HUDs, as well as the neural networks and how that all fits together. Just to give you a real brief background on Disti. So we've been around since about 1994, and we've got over 20 years of HMI solution experience in the market. We really got our start in aerospace and defense, but over the last 11 or 12 years, we've been growing very quickly in the automotive world. We are over 700 companies currently using GL Studio around the world. So we've got a pretty big footprint, a pretty big background in HMI. Just a real brief select customer list here. You'll see everybody from defense organizations to commercial OEMs, Boeing, Lockheed Martin, all the way out to Jaguar, Land Rover, Hyundai, Kia Motors, all using GL Studio for their HMI development and application. And just to give you a real brief idea of where our technology is employed, we're probably most well known for the adoption at Jaguar Land Rover over the last 8 years. But also in agricultural and Fendt. On the aerospace and defense side, we recently announced some new work with the T-7A Red Hawk at Boeing. Also the next gen avionics for Boom Aerospace, as well as a heads-up display for the L39 next gen with Spiel. So that one's very applicable to what we're going to be covering. Likewise with the Hyundai Mobis and Hyundai Kia Motors. We're used in everything from clusters to infotainment IVI style applications, as well as heads-up displays. So in order to do this, we need to have a pretty robust partner ecosystem. Everybody from different operating systems, RTOS providers like our friends at Green Hills and QNX and Wind River, out to all the different hardware providers such as NXP, Qualcomm, Telechips, Xilinx for a few. And of course, we also have a pretty wide ecosystem for our technical partners, Core AVI being one of our main partners, of course, but also we do quite a bit of work directly with ARM and a number of different standards committees as we support functional safety for avionics, automotive, nuclear facilities, medical, and industrial. So enough about DISTI. So I think in order to really cover an AR HUD, we kind of have to go back into the background of actually what's a HUD. So when you look at the first HUD, it's actually up for debate, and that's based on the conventional title for a HUD definition. It's either going to be the 1958 A5 Vigilante with North American Aviation is the name of the company, or it's going to be the 1961 Blackburn Buccaneer, which is previously Elliott Flight Automation, now BAE Systems. But either way you look at it, the first HUD was definitely in defense aviation. So the primary goal for the HUD is in aviation is to centralize all the flight critical data with the pilot's field of vision in order to increase the pilot's scan efficiency while reducing task saturation and information overload. So you'll see that these are also pretty prevalent in the automotive goals as well. But when we look at the first automotive HUD, again, this is up for debate based on your definition of what production means. So the first HUD in automotive actually showed up in the 1965 design for the Corvette XP, and then it showed up in the concept car in 1966. Now, shortly after, not shortly, about 20 years after, GM acquires Hughes Aviation, and within a few short years after that, the Oldsmobile Cutlass Supreme in 1988 produced 50 Indy pace cars with a built-in HUD. And so the definition is the difference between production here. It's either going to be a concept or a production vehicle, right? But again, either way, the first automotive HUD was seems to be credited to GM. So if we take that a step further and start looking at augmented reality and introducing augmented reality into a heads-up display, your heads-up display is typically your 2D overlay onto a specific screen. Whereas your AR, your augmented reality, really aims to overlay 3D warnings, hazards, points of interest, things that are critical to your driving into the 3D scene, actually embed them into the 3D scene. The primary goal to this is obviously to improve your safety, but much like with the aviation, it's really about giving the driver a scan efficiency of the environment while reducing the cognitive load. And so when we take a look at these two different markets of both HUDs and AR, you'll see that HUDs is actually expected to grow by 2026 at roughly 17.3%. And while this encompasses both defense and aviation as well as automotive, automotive is seen as a major contributor to this. Now, when we look at augmented reality, the augmented reality market is massive, and a lot of that has to do with consumer electronics, but automotive, of the dozen or so different markets, is also attributed to the increase in augmented reality adoption. So we're looking at roughly a 46.3% growth rate in that. And that is just a massive amount of new technology entering the market in a very short period of time. So luckily, we have the computing power, and the computing power just continues to get exponentially faster. So if you look back to when I started in graphics about 25 years ago, we needed a $250,000 reality engine from Silicon Graphics to process the kind of graphics today that can fit on a chip on the tip of your fingers. So a lot more pixels, a lot more clarity today, a lot more computing power for significantly less, which is also a great thing, given the complexity of the software that needs to go into these systems. So when you look at just 2017, there was a great study done by Visual Capitalist, where we're talking about the difference between a pacemaker, space shuttle, a couple of different types of aircraft and automobiles. When you look at the modern high-end automobile, you're looking at over 100 million lines of code. And so that level of detail and that level of development really requires higher level functional safety capable hardware as well. And so that brings us to the components and challenges of an AR engine. So if we go and start to take a look at the different pieces of an AR engine, now this is rather subjective, but in general, there are three different components here from the visualization standpoint. You've got your HUD distortion layer, you've got your spatial calibration layer, and then of course you've got my favorite part, which is the HMI visualization. Now, in the HUD distortion layer, this is where you're really trying to compensate for all the distortions caused by reflections or refraction of the light through your lens, your mirrors, your windshield, and of course, all the different models and vehicles will have slightly different changes or inconsistencies from one model to the next. So no two windshields are identical, and all of that needs to be accommodated in that HUD distortion layer. Likewise, the location of the driver's eye needs to be tracked or needs to be viewed, because if you're 10 inches to the left or 5 inches taller than the driver before you, you're going to be getting a different view through your viewing frustum as well. So when we take a look at the spatial calibration, we're really looking at taking objects and being able to transform them in 3D space, not just on a 2D display anymore. So you need to be able to transform the matrix and handle different orientations, scale, location, and then we need to be able to update that again based on head tracking information as well. And then finally, we get to the visualization layer, where we're really talking about rendering all those objects into the 3D scene. So we're not only taking into account the X and the Y location on a 2D aspect, but we need to be able to take into account the Z as well, which goes into or further away or closer to the viewer. And this is really where our specialty is. So when we look at what some of the challenges are for the AR HUD system, really the biggest one that we see coming up and in a number of different research studies has to do with field of view and depth of view. So your standard HUD is projecting onto a 2D or projecting onto a 2D screen, and it can have a much more narrow field of view and focus because you're not trying to overlay onto something further out into the scene, like a vehicle that might be 20 or 30 meters ahead of you. When you start to take into account 3D space, you really need to account for the volumetric data in your field of view. And because of that, the depth in that is significantly more important than it would be for a standard 2D HUD. Another challenge that you have is alignment limitations from your eyebox. So bigger hardware obviously becomes a lot more complex and more costly, and we're always trying to keep our hardware reasonable and small. The problem is here, in this case, if you have a eyebox alignment for a very small viewing frustum, and you've got two different heights for the drivers, well, they're not going to be seeing the exact same thing. And so you have to have a larger eye box, or you have to have eye tracking information that can make adjustments for you as well. So these are the types of issues that can cause defects in the pixels, defects in the line adjustments, contrasting issues, ghosting, warping, a number of different issues that are really just overcome by a larger eye box. But again, with that comes a bit more cost as well. And so there's a number of other challenges that you're going to face when developing your AR HUD. These are just some of the high-level views of that, everything from measurement tolerances to classification of those objects and how you determine what those objects are, if they're hazards or waypoints, if they're functional safety requirements attached to them or not. And then how do you track them? How do you continue to move that around in 3D space and be able to do it in a real-time fashion with low or no latency whatsoever, right? And of course, from the visualization standpoint, this all needs to be designed in a way that reduces or diminishes the cognitive load on the driver so that they can be more comfortable. And again, it's all about creating a safer environment, a safer way of driving. But as we know, the more technology we put into vehicles, the more options you have, the more challenges you have as well. So if we get into the visualization aspect of AR HUDs, of course, this is my favorite part. Now, with the visualization aspects, we're really trying to handle, well, mostly it's navigation cues, points of interest, and any safety critical information like hazards, warnings, and what your ASIL strategy might be for your safety case, right? So on the left-hand side, you can see we've got a relatively simpler view that still has the 3D content embedded into the scene. In this case, we're still getting cautions of other vehicles that are in the world. On the right side, we've got a whole lot more going on in a busy city set of streets and intersections. And the reason why we have these two images up here is one looks like it could be pretty beneficial, and it's relatively simplistic design. The other one, if you're ready for it, can still be extremely beneficial, but there is really a fine line between information overload and just enough information to be able to give the driver to say, here's a few critical things that you need to be able to consider at this moment while you're driving. And so these different types of 3D components really depend on what your design strategy looks like. So when you look at a tool like ours, like our GL Studio tool, you can really create any of these 3D components, embed them into the scene, attach data to them, be able to scale them, move them around in 3D space, such that you really have anything you need in the UX and UI design tool bag to be able to build your content up into 3D space. And then when we take a look at taking that content into the real world, a lot of this comes down to your real-time data processing and your functional safety strategy. That's going to define what you show, where you show it, and when you show it. So this really starts to lead our AR HUD discussion into the idea of functional safety and the idea of how do we compute all of this data? Where does this data go in the AR engine in order to get the information I need in a real-time and safety critical way so that I can then send it to the visualization layer and be able to show that data when and where we need to show it. But again, keep in mind, design judiciously, okay? There's definite use cases for AR. It's very, very clear. There are a number of research studies that we see out there that show benefits of augmented reality in the scene. There are case studies both for and against, of course, and it's all based on your cognitive load and what your design strategy is. And so that needs to be really taken into consideration. And so at this point, I'm going to conclude this part of the discussion So essentially, we're looking at a really rapid growth in the market for AR HUDs. We've already seen this in HUDs in general. HUDs and AR HUDs can definitely reduce your task saturation, reduce your cognitive load when paired with a good design strategy. Of course, there's a number of challenges in some of these new technologies, but nothing insurmountable. And there's just constantly new research that's going on to find the best possible path forward. So really, your appropriate level of design can really help with the safety aspects of your AR HUD. And so before I hand this over to Lucas, just wanted to point a couple things out real quick. DISTI has recently been added to the ARM Functional Safety Partner for tools and software, which is very excited. We're really proud to and honored to be part of that program. Also recently, if you look on our website, we've actually had several different adoptions from Hyundai Kia Motors, Hyundai Mobis for GL Studio and HUDs in production. So we're very excited and honored about that one as well. And then as we had mentioned earlier, in the aviation side, the L39NG is now adopted GL Studio for heads-up displays in the aircraft. Lucas and I, and also our friends at Global Logic, had written up a very detailed white paper. Lucas will cover a little bit of this towards the end of his presentation, but you're more than welcome to go and download that for free at glstudio.disti.com/ARHUD. And with that, I will go ahead and hand this over to Lucas for part 2, discussing more of the neural networks in automotive applications.
Okay, thank you very much, Chris. So let me just take over the presentation here. So my portion of the presentation is going to focus more on, why neural networks are a good application for AR HUDs, why they fit better than other algorithms that exist or other technologies that exist, and some of the functional safety requirements that come into place when we start talking about using neural networks for these types of applications, and what tools and software exist in the industry today to support these types of applications. So to start off, imagine we didn't know what neural networks were. Imagine that they were never discovered, or we hadn't done any research on them, and we needed to develop an algorithm that would detect cars in a scene. And from a high level, an approach we might take to doing this is first start looking at what edges exist in the scene. So where do we see objects beginning and ending? A good way to do this is to try to detect edges in the scene. There's a number of well-known algorithms that exist that don't depend on neural networks to do edge detection, that rely on different types of filters and standard deviations. And once we have this edge data in our scene, we can then start to try and find edges that match the outline of a car. So we would have to get many different models of cars from different angles and different perspectives, and start finding the outline that exists in the car and taking the edge data that we have from our edge processing algorithm to reinterpret these edges as a series of connected lines that make the outline of the vehicle that we're looking at. And we can take this outline and then start matching it against our database of different car outlines that we have seen and see if this outline matches those kinds of perspectives, and if there's any kind of deviance, what's our confidence that this object that we're looking at is a car. But then we start running into some problems. What if we're just looking at a picture of a car? So it's a car on a billboard, or it's a poster that has a picture of a car on it. Now we need to start looking at objects that are around the car or image that we're looking at to make sure it isn't a billboard, that it isn't a poster. So imagine we need to develop an algorithm to detect billboards in a scene. And as you can see, this is just going to keep going and going for the different conditions we need to detect vehicles in. So is there a better way where we can detect cars in a scene that are truly cars and not other objects without having to take into account all the different edge cases? And this is where neural networks really come in. So they are a class of algorithms and tools that excel at finding non-obvious patterns in data. So we can develop a neural network that takes in some data in any kind of format and prepare expected results and train a neural network to discover an algorithm that's capable of finding these patterns that are non-obvious. And the real benefit here is we start at the beginning with sample data and expected results, and we're discovering an algorithm along the process. So we don't know what the algorithm looks like at the beginning, but at the end we find one that is able to find these patterns in the scene. And how exactly does this fit in with our AR applications? Well, as Chris was mentioning, there's a lot of objects in a scene that we might want to detect in order to notify the driver of important information. So if there's hazards in the scene, such as pedestrians, we'll want to notify the driver that, oh, you know, this area, you have to be careful. There are pedestrians, you don't want to clip them with the side of your car. Or if there's other vehicles in the scene, to keep track of them to make sure that they aren't getting too close. And we'll want to use the detection data to, one, know what the object is, and two, know its position in the scene so that we can use the other algorithms that Chris had mentioned to actually determine how we need to project our augmented information on top of it, on top of the 2D data that we're receiving from a camera sensor, for example. Now that we know why neural networks are a good fit for AR HUD applications, let's talk about functional safety and neural networks. And when we're talking about functional safety and neural networks, there's two problems I think we need to focus on here. First, there's the expression of a neural network, and then there's the execution of a neural network. And the neural network needs to really be proved safe in both of these domains, where the expression of a neural network is really about what is the intent of the neural network? What is the problem it's trying to solve? What exactly is it trying to detect in a scene or track? And then the execution of a neural network comes down to when we actually deploy it on hardware, such as the embedded systems that run in a lot of cars today. Can we ensure that it uses a fixed amount of resources so that we know that when we provide data, we can expect a result in a certain amount of time so that there isn't unknown latency between when we receive sensor data from a camera or a LiDAR or something like that, and when we actually are able to detect objects in the scene, and that we don't use unknown quantities or undeterministic quantities of memory so that there isn't any kind of issues where we execute the neural network and then we crash the system because we're out of memory. So first, to focus on the expression of a neural network, there's a lot of research being done in this domain where we develop a level of confidence in what we're classifying. There's research being done into how we actually train the neural networks to make sure that they're trained properly in diverse environmental conditions, that the neural network is able to have the same performance in low visibility, or that the neural network is able to have the same performance when we're getting data from different sensors. So this touches back into the distortion that Chris was talking about. Not every camera is the same, not every lens is the same, and there can be deviations even within the same camera and the CMOS sensor. So we need to be sure that these deviations don't cause problems in the neural network, that the neural network doesn't focus on these deviations in its training. And the other thing that we want to be sure of is, can the neural network be tricked? So I'm sure everyone's seen videos before of neural networks or security researchers who have managed to trick neural networks by printing out special patterns on a piece of paper that make the neural network think it's seeing something or not seeing something. And so we need to make sure that these issues don't cause problems for our neural network, especially in the application that we want to specifically use it for. So like I mentioned before, this is a well-known area of research. There's a lot of focus being done on here to solve this problem. But something that we see in the industry is that this is the only problem that's being focused on, when it's not the only problem when it comes to using neural networks and applications that have requirements for functional safety. And safety isn't something that can just be added at the end of development. This needs to be focused on first. If researchers today solve the problems associated with the expression of neural networks and they do it entirely built on a platform that is inherently unsafe, the research will almost be effectively for nothing, since they won't actually be able to deploy those the fruits of their research in functionally safe applications. So this is why we think the execution of neural network is just as an important problem as the intention of neural networks, because when we're talking about functional safety and safety critical applications, the software and hardware needs to meet the existing safety standards that exist today in order to actually be deployed to those systems. And when you look at the neural network platforms and tools that exist today to do training, development, and deployment of neural networks, none of them are focusing on these functional safety standards. So for example, some really big tools that exist today that you might be familiar with are TensorFlow, PyTorch, Caffe, and these are, I would say, the industry standard tools for developing and training neural networks and then deploying them as well. And these are very great tools. They've had a lot of development time invested in them, but when it comes to deploying to a functionally safe system, we can't use them because we won't be able to get our certification at the end of the day. The other thing is, depending on the specific use of the neural network, our functional safety requirements will be different. When we're talking about an AR HUD application where it's just providing information to the driver and the driver is still in control of the vehicle, we're looking at an ASIL-B type classification of safety. So there's less functional safety requirements for the system overall. But if we start getting into systems where potentially neural networks are actually controlling the vehicle, we go into the domain of ASIL-D type safety applications, where there's a lot more stringent requirements that we have to prove that the system can't be manipulated and that it won't have errors that will cause hazards to the driver or other vehicles or pedestrians in the environment. So in order to better understand how functional safety and neural networks go together, it's important to actually understand what a neural network is doing at the end of the day. So I'm going to, at a high level, explain how the actual execution of a neural network works and how the training of a neural network works. But to start off, let's just go over what actually is a neural network. And some of you might be familiar with what neural networks are. Some of you might have a vague idea. But at the end of the day, a neural network is a collection of connected nodes that are grouped into layers. And these layers are connected to each other in different ways. And you might have heard terms like a fully connected layer or a convolutional layer. And this describes how the layer actually connects to other layers in the neural network and the purpose of that layer in the neural network. So in the example on the right here, this is a fully connected neural network. And the reason I'm using a fully connected neural network is because for explanation purposes, it's much simpler to explain compared to a convolutional neural network, for example. But if we were developing a neural network that was meant to do object classification or object detection, the CNN or convolutional neural network would be the neural network of choice for this, as research has shown that they have excellent performance when it comes to doing these specific types of applications. So a fully connected neural network is a neural network where the nodes in a layer are connected to each of the nodes in the other layers next to it. So if we look at this layer in the middle that I'm highlighting here, we can see that this node, for example, the node labeled F00 is connected to this node. It's also connected to this node, and it's connected to this one. And each other node in the network has the same connection properties. So the F01 is connected to this node, connected to this node, and connected to this node, and likewise for this one. And that makes it a fully connected layer. The other important properties of a neural network is that each layer has a value associated with it, and this is called the bias of the layer. And then each connection in the neural network has a value associated with it as well. So, and that value is called the weight. So if we look at the neural network, we can see that there's a connection between these two nodes. There will be a weight associated with that. Likewise for this connection between these two nodes. Likewise for this one, and then this entire layer would have a bias associated with it. And that really explains the structure and representation of a neural network. The other important question is, how we actually represent data in a neural network. So if we're talking about an AR HUD application, we're going to want to pass in very likely image data at the least coming in from a camera type sensor or even LiDAR data. And neural networks work on processing numbers, so we have to represent this camera data as a number in some way. And typically the way this is done is your image is represented by picture elements or pixels that make up the entire image, and there's a number associated with those pixels, where 0 typically represents no brightness for that pixel, and 1 represents full brightness or a white pixel. So if you look on the image on the right, you can see a very low resolution picture of a face, and you can see that each of the pixel elements in this low resolution face have a number associated with it. The higher the number, the more white the pixel is. The lower the number, the more black the pixel is. And this represents the brightness associated with that pixel. And you can do this for every color channel in an image. I'm sure many people in the audience have heard the terms RGB before, red, green, blue. So we can apply the same principle to the color channels in the image, where a red pixel has a value associated, or the red element in a pixel has a value associated with it, where 0 means no red at all and 1 means full red. Green, same thing, 0 means no green, 1 means full green, and then we can combine these values together to get a full color image. Now, how exactly does the neural network execute? Well, it's actually fairly straightforward. It's not doing anything groundbreaking or using advanced math or anything like that. The idea behind a neural network is that we take the inputs to the network. So if this is in a fully connected network, I'm representing the inputs on the left here, where each of these nodes would be a input tensor to the neural network, and there would be a number associated with that input. So in our AR HUD application, these numbers would be the pixel or the picture elements and the value associated with those picture elements. Each node in the neural network then needs to take a weighted sum of all of its inputs. So it's going to look at all of the inputs, every node that's connected to it, look at the value of that input and multiply that value by the weight that is on that connection. Once we take a sum of all these weighted inputs, we can apply the bias by adding it and compute a value for this node in the network by then applying this thing called an activation function. In the next slide, I'll focus a little bit more on the activation function, but it's just a simple function that's applied to whatever this resulting value is. And then we use that as the value for this node in the network, and we continue this process throughout the whole network, cascading the values down until we eventually reach the last layer in the network, which represents our output. And the output can really be anything. When we're talking about a object classification or detection, we usually want to have some value that represents what we think the object is from a list of objects. So it could be a car, it could be a plane, a pedestrian, it could be food, whatever it is. It depends how the neural network is trained. And then also the position of that object in the scene. So we'll want a number that represents the coordinates of the object in the scene so that we can put a bounding box around the object, for example. And typically when a neural network is implemented, we don't do this cascading sum process. There's more efficient ways to represent this. And those of you who are a little bit more familiar with neural networks might recognize this equation at the bottom, where we can represent this entire process of applying weight and bias as a series of linear equations that are then represented by matrix and vector multiplication and addition. And this really connects to how modern hardware actually implements neural networks. So the reason that neural networks make sense today and they didn't make sense, for example, 10 years ago is modern GPUs, NPUs, TPUs accelerate at doing this kind of linear algebra math very quickly and in parallel. So I mentioned cover the activation function a little bit more. So this is something that is applied to the calculated value for the node. In the previous slide, you should have seen that at the end of the equation, we applied this function here. And the idea behind an activation function is to introduce nonlinearity to the data that we're processing. And the idea behind introducing nonlinearity is so that we can find patterns that are nonlinear. If we're only looking for linear patterns, it wouldn't make sense to use a linear or to use a neural network. There's much better systems and algorithms that exist to find patterns that can be represented linearly. So we need to some method to introduce nonlinearity to the data that we're processing. A common activation function is the rectified linear unit, or ReLU. You might have heard this before, and it's a very simple function. If you ever wanted to know what it actually was, it's represented as a piecewise function where we're taking some input, and if that input is less than or equal to 0, we just output 0, and the input is greater than 0, then we just output the input unchanged. There's many different activation functions that exist. ReLU is a very common one because research has shown that has, in general, very good performance. But there's other activation functions you might have heard of in the past, such as the sigmoid function. There's the identity function as well. And so that explains really the math behind the execution of a neural network. And so the next thing I'm going to touch on now is the actual training of a neural network. So how do we quote unquote discover an algorithm? How do we get a neural network to discover an algorithm? And this really comes down to taking sample input. So we'll have, in the example of an AR HUD application, we might have pictures taken by the camera sensor that we're currently using that we want to train against. And we'll just pass it through our neural network and check what the results are. Initially, we'll set up our neural network so that each of the weights and biases associated with the network are randomly generated so that we have some number associated with them. And then we'll just pass our sample input in and check what the results are. And since this is a sample input, we should have the expected results of that input. What do we want the neural network to do for this input? And we'll compare it against what the neural network actually did for that input. And we'll compare, come up with a score for how well it did, and then adjust the weights and biases of the neural network to more closely approach or fit the expected results. And we'll keep doing this with hundreds, thousands, potentially even millions of different sample inputs, and repeat this adjusting process to better fit the neural network until we're satisfied with the results. And at that point, the neural network is considered trained, and then we can actually deploy it. So that covers kind of the idea of how neural networks actually function. So I'm going to go back into the topic of functional safety and how can neural networks be implemented in a functionally safe way. So like I mentioned before, there are a lot of common frameworks and tools that exist to develop, train, and deploy neural networks today. Some well-known ones are TensorFlow, PyTorch, Caffe. And a common element of these frameworks are that they require Python for the development and deployment of these neural networks. And if you're not familiar with Python, it is a open source scripting language, and it would be an extremely difficult component to certify. If you're aware of things that don't commonly get put in certification software, Python checks a lot of those things. For example, it uses dynamic memory management, which is usually a no-go in safety critical systems. It's a runtime interpreted programming language, which is usually a no-go in safety critical systems. You usually want to have it pre-processed to some degree as bytecode. Otherwise, you're certifying an entire interpreter or a compiler. And on top of that, it's an extremely large code base. It's over 150,000 lines of source code. So assuming it could actually be certified, that there were no major changes that would have to be done to it, there'd be a lot of effort associated with certifying that much source code. So an interesting standard that has recently emerged is the OpenVX standard from Khronos. And if those of you not familiar with Khronos, I'll touch a little bit more on them in the next slide. But it's a standard developed by Khronos that's designed for accelerating computer vision applications. So its core focus is on classical computer vision and modern computer vision. So it provides a number of classical filtering operations, but what's more interesting to us right now when we're talking about functional safety and neural networks is that it actually has a neural network feature set. And on top of that, it has two other feature sets that are desirable for neural network applications, especially when we're talking about functional safety applications. And that is the NNEF import extension and the safety critical deployment feature set. And I'll touch on those more in the following slides to get into to get into more detail about why they are valuable to us. But first, who is Khronos? If you haven't heard of Khronos before, it's a standards organization that develops a lot of standards, mainly associated with accelerating compute and graphics type applications. So they developed the OpenGL standard, the Vulkan standard, the OpenCL standard, and they have a safety critical working group that works to develop safety critical variants of these standards for functional safety applications. For example, there's an OpenGL SC standard, OpenGL safety critical, that's meant to be used in functionally safe applications. There's a Vulkan SC standard that's being developed today that is meant to be used in functional safety applications where you need access to both graphics and compute on accelerator devices like a GPU or an FPGA. And they also have a OpenVX SC feature set that they've defined for the use of OpenVX in functionally safe applications. So to start off, the neural network feature set is interesting from OpenVX. It provides functionality to build neural networks layer by layer. So it provides an API that allows you to construct convolutional layers, fully connected layers and different types of layers that you can then attach to tensors for the input and output of your program. So for example, if we are using a camera, we're likely using some library associated with that camera to get the data. It might be connected over PCI Express or some network, or using a camera standard like MIPI CSI. And so OpenVX puts no requirement on that. You can attach an input tensor to connect the data source to the actual neural network. And likewise, on the output, you can connect an output tensor that allows you to connect it to anything else in your application that needs to work with the data that's coming out of the neural network. And it provides several built-in activation functions. So like I mentioned before, there are some very common activation functions like ReLU, which is supported by OpenVX, but it supports a lot of the other very common activation functions, and it actually provides an extension capabilities to actually implement your own activation functions if you're using something that is non-standard. The next really interesting feature set of OpenVX is the NNEF import feature set, where NNEF stands for the Neural Network Exchange Format, which is another standard developed by Khronos. And the idea behind this is that Caffe, TensorFlow, these popular artificial intelligence, machine learning frameworks are popular for a reason. They exist because there's, developing training neural networks is not always straightforward. Any kind of assistance you can get is extremely valuable. But at the end of the day, these tools are really just defining a neural network. And like I mentioned before, a neural network in its definition isn't that complicated. It's a series of connected nodes where there's weights and biases associated with those connections. And it might be complicated from the standpoint that the neural network is very large, like it takes a large amount of data to represent that neural network. But the fundamental building blocks of it are not that complicated. So the idea behind Khronos's neural network exchange format is this is a common, well-versioned, well-understood format that isn't expected to randomly change, or not randomly change, sorry, but change without announcement, that implementers can depend on in their tooling to support neural networks that have been developed in TensorFlow and Caffe. So Khronos maintains a number of applications and scripts to take neural networks that exist in, for example, TensorFlow's proprietary format, export them to this common neural network exchange format that can then be imported into an OpenVX application. And this really provides a path to take existing neural networks that have been developed in these well-used industry standard tools and deploy them on a safety critical system that has safety critical requirements and functional safety requirements. The last interesting feature set is the safety critical deployment feature set. And this specifies a subset of deployment features within OpenVX that an application is supposed to target to reduce the certification burden of the application developers. So it really calls out the functions that you should use because there might be alternatives to those functions that would be difficult to certify in the end application. And so if applications focus on using the subset of functionality, they'll be more easily able to get the artifacts associated with their certification. The last thing I want to touch on is what Core VI is working on in this domain. So we have our VK Core SE product, and it's our own OpenVX 1.3 safety critical implementation. It's built on top of our safety critical Vulkan stack. So it's able to support all the different devices that Core AVI supports safety critical Vulkan on. And it does provide the image feature set, the neural network feature set, and the safety critical deployment feature set. And we target certification for ISO 26262, ASIL-D, DO178C, DAL-A for avionics applications, and IEC 61508 SIL-3 for industrial and robotic type applications. And I'll just touch on a little bit more on the white paper that Chris mentioned, and also what some things in the news for Core AVI. Core AVI is also an ARM functional safety partner. So if you look at the news links below, we're actually supporting the safety critical software stack for ARM's next generation Mali G78 AE GPUs. We've also recently announced a partnership with Intel to support their 11th gen Tiger Lake SoCs, both for safety critical hardware and the safety critical software stack as well. And if you're more interested in reading up on the topics that we've discussed in this presentation, I encourage you to go check out the white paper that Chris, myself, and Global Logic have worked on to get more details about the things that we've talked about in this presentation. And again, thank you for attending this presentation. It was a pleasure to present to you guys.
Thank you very much, Lucas, and thank you, Chris. That was a great presentation, lots of interesting stuff. I should mention that the white paper that we've been talking about is going to be emailed to all the registered attendees, so you will get that shortly. Okay, so let's move into our Q&A section. Question for Chris. You've mentioned functional safety several times. I would think that SOTIF would be even more important for this type of product. Is this so?
Yeah, so actually that's a great question. So for those of you who are not familiar, SOTIF is the safety of the intended function. It's really about the absence of risk because of hazards from unintended function or misuse, or I'll say reasonably foreseeable misuse. It's not directly solely applicable to HUDs or AR HUDs, but really kind of needs to be accommodated when you get to the safety case for your system. That question actually had a great follow-on for UL 4600 as well, and whether or not that should be supported. So that's really, from what I've seen, is not yet a standard, and really B, it's more applicable to autonomous vehicles. But from a visualization standpoint, again, something should be accommodated in the safety case. I mean, great question, or questions, I guess I'll say, but Lucas, you may have something additional from the neural networks point of view, maybe? I'm not sure.
So in terms of functional safety, what we've been talking about with the groups that we work with respect to functional safety is mainly around ISO 26262. I'm not as familiar with the SOTIF standards, so I think what you covered, Chris, really covers my understanding as well. Sure. And I'm not familiar at all with the UL 4600 standard, but it sounds like that it isn't fully developed yet.
Correct. Yeah, that's what I've surmised as well.
Okay, a question for Lucas. Which neural network is the best for object classification?
Hey, thank you for the question. So I touched on this a little bit during my presentation. So the example I gave was a fully connected network, but that's not typically what you'd use for object classification. In general, the best performance has been seen with convolutional neural networks, which use convolutional layers in their definition of the neural network. And those in general have had the best performance. But if you look at more recent research around neural networks, there's different types of neural networks that have had better performance for specific applications. But in general, convolutional neural networks have had the best performance for object classification.
Okay, thank you. Back over to Chris. From a visualization perspective, why do you consider depth to be such an important factor?
Yeah. So it's not really about me considering it. I'm kind of standing on the shoulders of giants. In order to prepare for this and to help write the white paper, I combed through a lot of different research papers, and they were all fascinating. And every single one of them brought up the #1 consideration as depth. But if you look at it logically, you know, the greater depth that you have in your system, that's going to increase your visual acuity. Yes, it'll certainly impact your processing requirements and your processing capabilities, but with better acuity, you're going to end up with a finer luminance, better chromaticity. You know, your uniformity gets better, your contrast gets better, and that really kind of relinquishes all of these artifacts that can be introduced into your scene, like that I was talking about earlier in the presentation, like, you know, ghosting, pixel misalignments, and it also depends really on the hardware technology that you're selecting as well. There's a lot to consider, but that's a great question. Thank you.
I do want to add a little bit to that question, Chris.
Sure.
There is ambiguity when you don't have depth information as well. I mean, even humans who have, you know, stereoscopic vision, we can get confused with depth when there's, you know, optical illusions. So being able to get real depth information of the scene that you're looking at really helps when you're projecting 3D information into that scene, so that you can actually place it at the right depth and it's not going to be confusing to the operator of a vehicle.
Yeah, absolutely.
Okay, Lucas, can OpenVX support any kind of neural network?
So in theory, yes, it can support any kind of neural network. It really comes down to how much work you want to put in. So OpenVX defines support for a number of standardized layers and activation functions. So it can definitely support any neural network that uses that set of layers or activation functions. It also is extendable, so you can actually add in your own code to implement other kinds of layers and other activation functions. So if you're willing to put in the work in to support less used activation functions or layer types, they can be added into OpenVX without modifying the standard.
Okay, and this one's for Chris. So on slide 21, you were showing very complex visual. Is this what you mean by cognitive overload? And how do you design visualization around that?
Wow. So slide 21 would be this guy. So yeah, the right side of that slide was exactly what I meant by cognitive overload. So just too much going on in the scene. You know, when you have the real world objects in the scene in a busy street, and then you have all of the warnings, all of the points of interest, all of your navigation cues coming up, and then on top of that, any of the safety related cues. There's really a lot going on there. So that the contrast I was trying to show in slide 21 was really about I'll say a minimalistic view that's showing what's really required versus a view that can show everything that you need, but do you really need to show all of that? So I guess the second part of that question was, can you say that second part of the question again?
How do you design visualization around it?
Wow. So that's a really loaded question. And so I'll say design is very subjective, a very subjective thing, right? And I'll say that probably every UX and UI designer out there or teams that are out there will have lots of collaboration bouncing back and forth. Ideally, it really needs to be part of the design strategy, and it needs to be agreed upon for sure, because it can certainly impact safety, there's no doubt.
Okay, great. And Lucas, why do you think most people in the industry are ignoring safe execution of neural networks?
That's a great question. I think it's not as interesting. Well, there's a couple answers. One, I don't think it's as interesting as of a problem to solve. It's not the flashy problem to solve. The other thing is I think a lot of people in the industry who are working with neural networks aren't people who have had to do functional safety applications in the past before. So we at CoreVI, like DISD, have been working in the avionics industry for a long time where safety critical requirements have been a lot more prevalent than they have been in automobiles. And so when we see an application that wants to be used in safety critical applications, we look at it and we think, oh, is the entire stack safety critical? Because if it's not, it doesn't matter what you have on top if it's safe or not, because you can't actually deploy it to your system. And so I don't think the bigger players who are working on neural network research right now have that same perspective from working with safety critical systems for a long time.
Okay, and here's another one for you. Is your OpenVXSC implementation able to utilize off CPU or GPU hardware? If so, what silicon options are available?
Yes, so our OpenVXSC implementation does target off CPU hardware. So in my slides, I mentioned that it's developed on top of our Vulkan safety critical stack. So it actually targets a Vulkan safety critical driver, and we at CoreVI support a number of different silicon options for our Vulkan safety critical driver, including AMD's Polaris GPUs, Vivante's GC7000. So that's the GPU on the i.MX8 Quad Max. In the new slide that you can see on the presentation right now, we've recently announced support for Intel's 11th gen Tiger Lake SoCs. So we'd be supporting running OpenVX on the GPU of that Tiger Lake SoC. And then likewise for ARM's next generation Mali G78AE, which is interesting because it's one of the first designed GPUs with functional safety, actually a hardware requirement for the GPU. But yeah, so we have support for that as well.
Okay, and someone is wondering who provides the NNEF conversion tool?
So the NNEF conversion tools are maintained by Kronos. They have it publicly on their GitHub page, so you can go check them out if you want to see them. And then the OpenVX implementations would work from that point onward. So after you've used Kronos's NNEF conversion tools to actually convert the neural networks.
Okay, and for Chris, do you see many requirements out there for HUDs and for AR specifically?
So we see lots of HUD requirements that are out there. AR, we've seen a few AR requirements in production, but they're very limited in scope currently. But what we are seeing is a lot of AR requirements in research and development. That's really ramping up like crazy. I mean, you've seen in our press that we were showing the Hyundai Kia Motors and the Hyundai Mobis adopting us for HUDs as well. So we are seeing an uptick in HUDs, and it's really about keeping people's eyes on the road and not so much heads down, right? More of a heads up view. So yes, we're seeing more HUDs requirement in production. We're starting to see more AR HUDs requirement in R&D currently.
Okay, great, thank you. And we're over time, but one last question. How well does the system handle degradation of the camera as it gets dirty, scratched, etc.? I assume that this system is trained before deployment rather than adapting in the field.
So I think this is a question I can answer. And I think the person who asked the question is exactly right with their assumption. Depending on the use of the safety critical system, at a minimum, the neural network should be trained to know that quality of data that it's getting from the sensor is unusable, so that it can report to the system that it can't make any determination about what's going on. And then the system can respond by notifying the driver that the system is turned off. Or depending on how dirty it is, the neural network could be trained such that it's able to actually operate with those dirty conditions as well.
Yeah, Lucas, if I could, I'd like to add something to that as well. I think that the question also definitely depends on the design of the system. There may be redundant pieces in the system as well, that could augment the data that's going into the brains of it.
Yeah, that's exactly correct. I don't think you would rely on a single camera sensor for your entire system, especially if it's a system with functional safety requirements. You would likely have some redundancy there for gathering data.
Okay, great. Well, that's all the time we've got for now, and I thank everybody for joining us today. We're so happy that you came to listen to our webinar. We will be sending the links out from the presentation in the email with the white paper, so you'll get the links that way. Otherwise, thank you, Lucas. Thank you, Chris, and I hope everybody enjoyed our time together today. Please reach out if you have any further questions, and have a great rest of your day.
Thanks, everybody.
Thank you.